So in our last lesson, we discussed Lagrange's theorem. So specifically, if we have a polynomial f of x whose coefficients are in a field, then if the degree of that polynomial is degree d, then we have at most d roots in that field. Using Lagrange's theorem, we did a new proof of Wilson's theorem, but then afterwards we covered this result of Gauss, and so specifically this proposition, which says that if we have a prime number p, m is a natural number, and we're considering the equation x to the m is equal to 1 bar in the integers modulo p, then we have that if m divides p minus 1, we have exactly m solutions, and in general, we have GCD of m comma p minus 1 solutions. And I mentioned in that video that this is a precursor to what will become known as Lagrange's theorem in abstract algebra. Today we're going to follow this result of Gauss, and so in Gauss's Discusiones Arithmeticae, this proposition was essentially a lemma in the direction of the primitive root theorem, which is the goal of today's lesson. So to get us motivated to what is the primitive root theorem, let's recall the following. So if we have an element, a bar, in the integers modulo p, and we define it more generally for the integers modulo n, but today we're going to be working over the integers modulo p for p a prime, then we know that the order of a bar is the smallest natural number so let's say smallest natural number k, such that a bar to the k is equal to 1 bar. So now we know by Fermat's little theorem, a bar to the p minus 1 is equal to 1 bar for each a bar for each non-zero a bar. So all the non-zero, so in other words, all those elements a that are relatively prime to p, we have that a bar to the p minus 1 is equal to 1 bar. This led Gauss to ask the following question. Is there a congruence class in the integers modulo p such that the order of n bar is exactly p minus 1. We already know by Fermat's little theorem that we always have p to the p minus 1 is equal to 1 bar, and as a consequence, the order of every element of the integers modulo p has to divide p minus 1. But now we want to know, do we have equality? And the answer is yes. And so this is what we call the primitive root theorem. And that's the goal for today's lesson, is to prove this result. So let's go ahead and get started. So let's go ahead and make a definition. So we're fixing p as a prime. We have a congruence class a bar in the integers modulo p, which is non-zero. We will say that a bar is a primitive root in the integers modulo p if the order of a bar is equal to p minus 1. And so we may say that the integer a is a primitive root modulo p. And so the question we just phrased over here is equivalent to asking, if we are working over the integers modulo p, is there a primitive root? So our first proof towards this direction is the following statement, which says that if we assume that we have a primitive root, so right now we're assuming the existence of such a primitive root, then every non-zero element of the integers modulo p appears once in the following list, where we have a bar to the 1, a bar to the 2, all the way to a bar to the p minus 1. So let's go ahead and consider the set. So proof, let S be the set a bar to the 0, a bar to the 1, a bar to the p minus 2. So we have this here. By construction, we have that S bar is a subset of the integers modulo p. So we have this here. And from structures, we know we have a finite set. The cardinality of S is going to be at most the cardinality of the integers modulo p. But now we're looking at the non-zero elements. So let's go ahead and look at the integers modulo p minus the congruence class of 0. We know that the integers modulo p minus the congruence class of 0, that's going to give us p minus 1 elements. So we know that the right-hand side has exactly p minus 1 element, so that's the cardinality of this set. We know that the cardinality of S is going to be at most p minus 1, since there are p minus 1 elements in this set. So moreover, the cardinality of S is going to be at most p minus 1. Therefore, it suffices to show that the cardinality of S is equal to p minus 1. And so let me just go ahead and put it over here. So we're looking at the non-zero elements. So just replace. So we have that this subset containment. And so since S bar being contained in here would imply that S is equal to the integers modulo p minus the congruence class for 0. And so that's what we are going to do. We are going to prove that there are exactly p minus 1 elements. So what must happen if this were not the case? That would mean that there would be at least 2 of these elements so that they would be equal. So let us go ahead and do that. And we're going to be doing this directly. So suppose that a bar to the k is equal to a bar to the j for, now k and j are going to be between 0 and p minus 2. So this is our assumption. So we're assuming that this is true. And what we want to show is that then k must be equal to j. And if that's the case, then every single element in here is distinct. Well, if we have this equality, we know that a bar is non-zero, so it's a reduced residue of the integers modulo p. So since a bar is a reduced residue, and the product of reduced residues is a reduced residue, that a bar to the k is a reduced residue, and therefore we have a multiplicative inverse for a bar to the k. But we can now go ahead and multiply both sides of the previous equation. So we have a bar to the k is equal a bar to the j. We're going to multiply both sides by a bar to the minus k. And so now this here would imply that we have a bar to the 0, which is 1 bar, is equal to a to the j minus k. So we have this here. Now, but then, j minus k is divisible by the order of A, by lemma from the last lesson. We have that the order of A bar divides j minus k, but A bar is assumed to be a primitive root, so that means that the order of A bar is equal to p minus 1. So we have p minus 1 divides j minus k. And so we have this here. But now, if that's the case, that means that j is congruent to k modulo p minus 1. So we have this congruence over here. So they're in the same congruence class, but what's the problem with this? Well, our assumption is that k and j are both between 0 and p minus 2. But now we have that they're in the same congruence class, so we know that there is a representative for j and k that we can... So under this assumption, k is an element between 0 and p minus 2, and so is j. So they must be exactly equal. Since we have this inequality here, we conclude that j is equal to k, and so we have that if we started off with any two elements in here that were equal, then they really are the same element. And so that now implies that if a to the k, if we have distinct k and j's, we have two distinct elements in S. So consequently, a bar to the j, so consequently a bar to the j does not equal a bar to the k if j does not equal k. And here, of course, we're making the assumption that the j's and k's are between 0 and p minus 2. So this implies that the cardinality of S is equal to p minus 1, which concludes the proof, as that's what we said that it suffices to show. And so now we're done. We have proven the proposition that is going to get us one step closer to proving the primitive root theorem. And so this was also part of Gauss's disquisitiones arithmeticae and his original argument for proving the primitive root theorem. And so the key thing is we have the cardinality of S is p minus 1. We know that we are in the integers modulo p minus the congruence class of 0, so that has p minus 1 elements, and so the cardinalities of both of these sets has to be exactly the same. Since the cardinality is the same as the 2, S is equal to the integers modulo p minus 0, so that tells us that every element of the integers modulo p minus 0 appears exactly once in that list. And so we are done. We have proven the proposition. So the next result we are going to prove is the following lemma. So now we're going to take p and q to be prime numbers, s to be a natural number, and we are going to assume that q to the s divides p minus 1. So in other words, this is also saying that q and p have to be distinct primes. And we want to show that if q to the s divides p minus 1, then we can find an element of the integers modulo p whose order is q to the s. So how do we prove this? So we're going to construct two sets for the proof. And so the way that we're going to construct these sets is by looking at those elements that upon raising to the q to the s, we get back 1 bar. And similarly, those elements, if we raise to the q to the s minus 1, we also get 1 bar. So let's go ahead and let t1 be the collection of elements of the integers modulo p, such that if we raise a bar to the q to the s, we get back 1 bar. And we're going to let t2 be the collection of those elements of the integers modulo p, such that if we raise a bar to the q, but now it will be the q is raised to the s minus 1, so that this is equal to 1 bar. So what do we know about these two sets? Well, from last time, we already have the information for the cardinality, because in this case, we are given that q to the s divides p minus 1. Since q to the s divides p minus 1, we have that, or we have by the proposition from last time, so this is proposition in the book 10.2.2, that the cardinality of T1, that is so the number of elements that satisfy this equation is exactly going to be q to the s, where now we take m to be q to the s. So we have that this here is going to be exactly q to the s, but we also have that if q to the s, and similarly, let me just write this down, so similarly, q to the s minus 1, well, q to the s minus 1 divides q to the s, because it's just going to be q to the s minus 1 times q to the s. So this also divides p minus 1. And so the cardinality of T2 is q to the s minus 1. And so this cardinality is strictly smaller than that of T1. But what we want to show is that T1 properly contains T2. So now next, we claim that T2, so I said properly, but we just, for this proof, we just need T, that this is a subset. So let's go ahead and show that T sub 2 is a subset of T1. So we're going to do this in the standard fashion. We're going to choose an element of T2. So let a bar be in T2. Then, by definition of what it means to be in T2, that means that we can raise a bar to the q to the s minus 1, and we get back 1 bar. So that's what that means. But now what we want to show is that that we can go ahead, and if we raise it to the q to the s, that we also get back 1 bar. So that's what it suffices to show. So now consider a bar to the q to the s. So this is the hope. The hope is that this is 1. Well, we can go ahead and separate this. This is a bar q to the s. And so we break this up with q to the s minus 1. That will be the same as multiplying this with a q to the 1 power. So we have this here. But exponent rules tells us that this is the same as taking a bar to the q to the s minus 1 and then raising all of this to the q. But if that will be, now the inside is going to be 1 bar. So we have 1 bar to the q, which is 1 bar. Thus, we have that a bar is contained in T1, and so we have the containment we want, and T2 is contained in T1. And since q to the s minus 1 is strictly less than q to the s, we have the stronger statement that T2 is properly contained in T1. And so now we're going to do the clever trick. We know that this is properly contained. So if we take the set difference of T1 with T2, it's non-empty. So T1 minus T2, the set difference, this is a non-empty set. So what happens if we choose something in here? So now let's go ahead and choose our A bar. Actually, we've been using A bar for quite a bit. Let's go ahead and call the next element B bar. So let's choose an element in the difference of T1 minus T2. So we have this here. So an element in here has the following property. So this tells us that then B bar to the Q to the S is equal to 1 bar, and B bar to the Q to the S minus 1 is not equal to 1 bar. So that's what it means to be in that set difference. So where do we go from here? If we look at the proposition from last time, we know that A bar to the S is equal to 1 bar if and only if the order of A bar divides S. So this tells us right now that because B bar to the QS is equal to 1 bar, we have that the order of B bar divides Q to the S. So by proposition, from the book 10.1.3, we have that the order of B bar divides Q to the S. So we have this here. But Q is prime. So if Q is prime, and we know that the order of B is a natural number, so we have a natural number dividing Q to the S. And so since Q is prime, this divisibility that the order of B bar is equal to Q bar to the J for J having the following inequality. We can go from 0 less than or equal to J all the way to S. And so here's where we are now going to use that we have that B bar to the QS minus 1 is not equal to 1 bar. Because now, if we take the contrapositive of this statement, that's negating this equivalent statement. So if we take the negation of both, so let me just write contrapositive, but the contrapositive with the equivalence of both, so this is going to be that A bar to the S does not equal 1 bar if and only if the order of A bar does not divide S. So let's use this statement right here with this here. So by the negation of, let me write contrapositive instead. That's more precise. By the contrapositive of proposition 10.1.3 and B bar to the Q to the S minus 1 not equal to 1 bar, we deduce that Q, that the order of B bar, which is equal now to Q to the J, one typo, that was supposed to be a Q, I just noticed a typo over here, I have written Q bar, Q is now a natural number, there's no need for a bar there, so I apologize. So we have order of B bar is equal to Q to the J. This does not divide Q to the S minus 1. So therefore, the exponent J, because it divides Q to the S, has to be exactly S, which concludes the proof. And so that finishes it off, because now J must be equal to S, but then we have that the order of b bar is q to the s, which shows the existence of an element whose order is q to the s in the integers modulo p. And so we have our result here for this lemma of Gauss. So now we are one lemma away from proving the primitive root theorem. So here's what the lemma states. We have a natural number n, and we have that a bar and b bar are in the integers modulo n. And if they are reduced residues, then we have that if the order of a bar and the order of b bar are relatively prime, then the order of ab quantity bar is equal to order of a bar times order of b bar. So something to keep in mind is, for primitive root theorem, we're working in the integers modulo p. Over here, we're giving a more general statement because we're proving that this holds over the integers modulo n whenever we have that the order of a and the order of b bar are relatively prime. So let's go ahead and prove this. And so the main tool is going to be this proposition being used several times. So to make notation simpler, let's go ahead and let r to equal the order of a bar, s to be the order of b bar, and k to be the order of ab bar. So that's going to be the notation we are going to have. And the first thing we are going to do is take a bar to the r times s. So if we have order, so if we take a bar to the r times s, by exponent rules, this is the same as taking a bar to the rs, b bar to the rs. But if we do exponent rules once more, we can rearrange this. So we know that the order of a bar is r, so we're going to do r, and then we're going to have an s on the outside. And similarly for b bar, since its order is s, we're going to have s on the inside, r on the outside. And so we are just doing 1 bar to the s times 1 bar to the r, but this is all 1 bar. And so this is equal to 1 bar. So by proposition from the book, so 10.1.3, we know that if we raise AB bar to the RS, that this is equal to 1 bar. But now that tells us that the order of AB bar has to divide R times S. And so the order of AB bar, that's K. So we have that K divides RS. And if K divides RS, we know in particular we have that K is less than or equal to R times S. And so now what we want to show to prove this, we're going to show that RS is greater than or equal to K. So it suffices to show that RS is less than or equal to K. So if we show this, we are done, because we already have this inequality here. So this will tell us that RS must be equal to K. Let's just write that down. And so this is the trichotomy property of the integers. So how do we go about showing this? So the key thing is, we're going to go about the same way that we did over here in a clever fashion. So here's how. So we're going to observe the following. So if we start, I'm going to do two different equations. So we're going to have AB bar. So we know that we're going to have it here to the K, and down here we're going to have it also to the K. The order of AB bar is K, so we know that both of these are going to be 1 bar. If we raise both of these equations to some natural number exponent, we're going to have that they are also going to be 1 bar. So we can go ahead and say the following. So I'm going to go ahead, raise both sides, but the 1 bar is going to stay the same. The first one, I'm going to raise it to the R. The bottom one, I'm going to raise it to the S. So now this here, we can go ahead and do by exponent rules. This will be a bar to the kr, b bar to the kr. We know that r is the order of a bar, so we're going to have a bar to the r to the k times b bar to the kr. And so this is going to be 1 bar to the k, b bar to the kr. And so we just have b bar to the kr. And if we look at the bottom equation, this is going to be the same thing, but now it will be ks instead and b bar ks. But now s is the order of b bar. And so let's go ahead and write this as the ks here, and then we have b bar raised to the s first, and then to the k. And so this is going to give us a bar to the ks, and then 1 bar to the k. And so this is just going to be a bar to the ks. So we have these here. If we apply proposition 10(1)(3) once more, we then have that because b bar to the kr is equal to 1 bar, then this tells us that the order of b bar has to divide kr. And so the order of b bar, that's going to be s, so s divides kr. And we also have from the second one over here that this is a bar to the ks is equal to 1 bar. Proposition 10(1)(3) in that situation tells us that the order of a bar, which is r, divides ks. So we have this here. But we know that s and r are relatively prime. That's part of our assumption, that the order of a bar and the order of b bar are relatively prime. So we know that r and s are relatively prime. And so since the GCD of r and s is equal to 1, Euclid's lemma, and so when I say Euclid's lemma here, I mean the one in the book. So recall that the original Euclid's lemma pertains to primes, but then in the book, we prove what the book calls Euclid's lemma tells us that if s divides kr, but s is relatively prime to r, then s divides k. And similarly, that argument over here tells us that r divides k. And so Euclid's lemma, the book form, implies that s divides k and r divides k. So consequently, since they are relatively prime, we have that rs divides k. But if rs divides k, that means that rs is less than or equal to k, which concludes the proof. As now we have by dichotomy, as we asserted above, that if rs is less than or equal to k, then dichotomy will tell us that we in fact have equality. And so we are done with this proof. And now we can prove the primitive root theorem. So now we're going to go ahead, use the previous 2 lemmas we have done to prove the primitive root theorem. And the good thing is we've already done the heavy lifting. It's just a matter of arranging these 2 results, these 2 previous lemmas, in a way that the primitive root theorem will follow almost automatically. So here's just as a recap, we're fixing a prime number p, and we want to show that there exists a primitive root modulo p. So in other words, we want to show that there exists a congruence class in the integers modulo p, such that the order of that congruence class is exactly equal to p minus 1. I'll make a comment for those of you who have taken abstract algebra. What the primitive root theorem states is that if we look at the integers modulo p as a multiplicative group, then it is cyclic. And so specifically we can find an element that will generate that group. And so that's really how this connects in the generalization to Lagrange's theorem. But let's go ahead and prove this version. So now we want to show this existence. So how do we go about this? Well, we're going to consider the oddest prime of them all first, 2. So we're going to first look at 2 and then look at the rest, because 2 is the simplest case to look at, and doesn't behave like the rest. So let p equals to 2. So if p is equal to 2, then the integers modulo 2 is just going to consist of 0 bar and 1 bar. And the order of 1 bar is equal to 1, which is 2 minus 1. And so we have that the theorem holds. So we've done one part. So now we can go ahead and suppose that we have that p is odd. So I'll write this below. P is odd. And what we are going to do is consider the prime factorization of p minus 1. So let p minus 1 be given by the prime factorization going from 1 to k of pj to the aj, where each p sub j is a distinct prime. And so observe that the reason we want to eliminate 2 is that we would be in trouble had we done it this way, because then we would have 2 minus 1, which is 1, but 1 is not prime and doesn't factor into primes. And so now, because this is at least 3, we know that we will always have that this can be written as a product of primes uniquely. And so we have this here. So where each pj is a distinct prime. But now which result can we use from the ones we have proven at this point? So we know from lemma 10.3.4 that if we have that, so we're working over the integers modulo p, so if we have any other prime q, and we know that q to the s divides p minus 1, there is an element of order q to the s in zp. So let's use that lemma. So by lemma 10.3.4, there exists an x sub j in the integers modulo p. To be precise, so by lemma 10.3.4, we have that for each j, there exists an element x sub j in the integers modulo p such that the order of x sub j is equal to pj to the a sub j, since that's the exponent appearing here. So we have that p to the p sub j to the a sub j divides p minus 1. So we have this element here. So we have the existence of x sub j's. But now let's go ahead and take the product of all these x sub j's. So let x equal the product from j equals 1 to k of the x sub j's. So this is our element, x. Then, by the lemma 10.3.5, and one of the homework questions will have you just show that this extends to it being multiplicative over a product, and this is just the inductive step. So we actually have, as a consequence of lemma 10.3.5, that the order of x bar, oops, and I forgot the bars on the front here. So we have these. So we have that the order of x bar is going to be equal to the order from j equals 1 to k of the orders of x sub j bars. But we know by construction that each of these is pj to the aj. But this is just equal to p minus 1 by construction. And so we have that there is an element of order exactly p minus 1. And so now we are done with the primitive root theorem, and so we have established this result. And it is this primitive root theorem, along with the works of Gauss that we have shown, that eventually would lead to a mass generalization, which is covered in abstract algebra. So the primitive root theorem tells us that if we have the integers modulo p, where p is prime, we can find at least one primitive root. Now we're going to go ahead and answer the following question. Well, we know the existence of at least one, but how many are there? And so that's the goal of the next theorem, is to prove exactly how many primitive roots there are modulo for the integers modulo p. So the first result we're going to prove in that direction is the following lemma. And so what it says is, if p is a prime number, a bar is a congruence class in the integers modulo p, which is a primitive root. Then for any integer j, we have the congruence class of a to the j is a primitive root if and only if j and p minus 1 are relatively prime. So how do we prove this? So I'm only going to prove the case when j is a natural number, and the case for j being an integer, that will be left as a homework question. So we show the case when j is a natural number. Well, in this case, we can go ahead and use the lemma that we had for homework assignment, so lemma 10.1.6, which tells us that if we have a congruence class a bar in the integers modulo n, which is a reduced residue, and the order of a bar is given by s, then the order of a bar to the j is s over the GCD of j and s. So now with that in mind, we get the following. So assume that a bar to the j is a primitive root. Then it is the case that the order of a bar to the j, by definition, this is going to be p minus 1, since it is a primitive root. But now, if we apply lemma 10.1.6, here we have order of a bar, and so we're going to have order of a bar, but the order of a bar is a primitive root by assumption, so we just can go ahead and write, instead of writing order of a bar, we have that this is going to be p minus 1 over the GCD of j with p minus 1. But now we have that p minus 1 equals p minus 1 over the GCD, which is equivalent to saying that the GCD of j and p minus 1 is equal to 1, and so that finishes it off for j is a natural number. And then for homework, you will show the case when j is less than or equal to 0. I'll just mention a couple of remarks. Note that if j is equal to 0, then a to the 0 is going to be 1 bar, and 1 bar is a primitive root if and only if p is equal to 2. And so that's just something to be mindful there. And then for the negative case, the argument is a matter of realizing if we have a to the negative exponent is a primitive root, then a to the negative k, that's just the multiplicative inverse of a to the k. And so what you want to do for that case is consider how the multiplicative inverse of a is related to, the multiplicative inverse of a to the j is related to the multiplicative inverse of a to the negative j. And so that way you can return it back to this lemma, to the case we just showed. And so, but for our purposes, the case when j is a natural number will suffice for proving the next statement, which is the one that tells us exactly how many primitive roots there are for the integers modulo p. And the great thing is we have already done the heavy lifting. So I just went ahead and added a statement that we are going to need to prove this. So by the primitive root theorem, there exists a bar in the integers modulo p such that a bar is a primitive root. Now, by proposition 10.3.2, we have that if we consider the list, so we have that the integers modulo p minus the congruence class of 0, this is the same as a bar to the 0, a bar to the 1, a bar to the 2, all the way to a bar to the p minus 2. So all the non-zero elements of the integers modulo p appear in this set. And we know that they are all distinct by the proposition, so we have this. By the lemma that we just proved, and so this is lemma 10.3.6, we have that a bar to the j is a primitive root if and only if the GCD of j and p minus 1 is equal to 1. So we have this here. But there are exactly phi, so that's the definition of the Euler phi function. So there are exactly phi of p minus 1 j's satisfying GCD of j p minus 1 being equal to 1 by definition. And so now that concludes the proof. And so now we're done. Since we have all the exponents over here, so if we want to know which ones are the primitive roots, we just have to focus on those exponents. And that's what we do with lemma 10.3.6. And so we're looking at those j's in the exponent that are relatively prime to p minus 1, but the Euler phi function allows us to count those exponents j being relatively prime. So that's precisely phi of p minus 1, and we are done. We have proven that there's phi of p minus 1 primitive root for the integers modulo p. And so the next lesson is going to have us continue forward into what is known as quadratic residues and building up to what is one of the most famous results of the 1800s, the law of quadratic reciprocity. And in the process, towards the end of this week and then next Monday, we will have the tools to be able to prove the Fermat sums of squares theorem. So specifically those primes that when we reduce them modulo 4, the remainder is 1. And so Fermat claimed that the primes primes which are congruent to 1 mod 4 can always be written as a sum of squares, and it's a if and only if. And so that went unproven until Euler. And so by Monday we will have completed the original proof that Euler did. And so that's where we are going to be building up to. But to do that, we need to understand how do the squares modulo p behave. And that's going to be the focus for our next several lessons.